Welcome back, and in this series of videos we're going to be looking at Redox 3, that's Redox Equilibria. This is the application of redox to cells and batteries and how we can use chemistry to make our cells and batteries work better, including hydrogen fuel cells. So you're going to need your notes, and we're going to skip the first practical, which you're going to do in class, so we're going to pick up the notes on page 2. So if we take a metal such as zinc and we put it in contact with its own ions, zinc 2+, we get an equilibrium position set up. But because zinc is a very reactive metal, the position of equilibrium lies well over to the right-hand side. So this is to the right. And that's because zinc is a very reactive metal. It has a tendency to donate its electrons, and that leaves the surface of the metal with a negative charge. Zinc is said to have a negative electrode potential. Now, this is redox, and you should remember right back from lower sixth, you can't have an oxidation reaction on its own. You also need a reduction reaction. So batteries are exactly the same. Zinc on its own is not going to make a battery. This is a good source of electrons, but I also need a sink of electrons. So as well as a source, I need a sink of electrons. In other words, if this is my oxidation reaction, I need a reduction reaction to act as my sink of electrons. If I do the same thing with copper, again, still a reactive metal, but this time if I set up this equilibrium, it lies over to the left-hand side compared to most other metals, or at least compared to zinc. And this is because the copper is not such a reactive metal. So if we have these two reactions set up, I've got zinc in this beaker, zinc solution and a zinc rod, and in this solution I've got copper solution and a copper rod. Well, on the surface of the zinc here there are going to be spare electrons, so there are electrons, so it has a negative charge. So if you like, that, remember, is my source of electrons. On the other side I have my copper rod, and that is going to be my sink of electrons. We call this a positive because it accepts electrons. So I have my source on this side and my sink on this side. And if I can connect these two half cells together, I should get my electrons to flow from my source around and on to my sink. And that flow of electrons, that's my current. And I can use that to power everything from a car to a mobile phone. So at the bottom of page 4, we have this standard electrode potential chart going from magnesium on one side down to silver on the other side. So it's not possible to measure the electrode potential of a half cell in isolation. So we don't know what the absolute value of this is. We can only measure a potential difference, which means we have to have something to compare everything to. Now, the standard electrode which we compare everything to is this one, is the hydrogen electrode, and we give that a value of 0, and then we compare everything to that. So we have my hydrogen electrode as my left-hand electrode, and we compare everything to it, whether it's better or worse than hydrogen at gaining electrons. So our definition of a standard electrode potential of a standard half cell is the potential of that half cell, be it copper or zinc, relative to our standard. And our standard is our standard hydrogen half cell. And it's important that we quote the conditions. So it's 100 kPa, 298 Kelvin, and all solutions are 1 mole per decimeter cubed, so concentration of 1. So this is the setup for a standard hydrogen electrode. We've got our hydrogen gas at the right pressure, we've got temperature, we've got the concentration of the hydrogen ions as 1 molar. Notice also the electrode that we're using. We're using a platinum electrode coated in platinum black. That's because you've got the reaction between a gas and a solution. So this is simply providing me with a surface on which the reaction needs to take place. Now it's important that this is not a reactive metal, that this doesn't take part in the reaction. It is simply there as a surface. If this was a reactive metal, you would have 3 different components, and we just want to compare hydrogen ions to the hydrogen gas. You do need to watch these ones because it's very easy to miss this. But for example here, sulfuric acid of concentration 1 would be unsuitable because sulfuric acid is a diprotic acid. So 1 molar H2SO4 would actually release 2 moles of hydrogen ions. So because it's this diprotic acid, 1 molar H2SO4 would be near enough 2 molar hydrogen ions. So it's important that you watch that one. Remember, all solutions that we're measuring must be 1 molar. So this is a demonstration you're going to see in class, and this is a very straightforward cell. It's called the Daniell cell, and you've got a zinc half cell and a copper half cell. And what you should notice is that you connect it up and nothing happens until you add the salt bridge. And it's quite difficult to understand what's going on here, so I'm going to take you through it in a couple of steps. So this is my cathode. At this side, because of the position of the equilibrium position, the Cu2+ ions are gaining electrons. Notice the electrons are flowing this way round, and they are going to make copper. Okay, so that's the reaction that's going on there. Now, this obviously copper 2+ ions doesn't exist on its own. You probably also have either some sulfate or some other negative ions. Let's have a look what's happening on this side. So this is my source of electrons. My zinc is being oxidized to zinc 2+ and my electrons. And again, that zinc is probably not on its own, or the zinc 2+. The solution here, remember, because it's in equilibrium position, you've also probably got some negative ions. Let's make them again, sulfate ions, 2-. Now, the problem on this side is that as the 2+ ions turn into copper, there's no change in the concentration of the sulfate ions. So you're losing 2+ to become Cu, but this concentration stays the same. On the other side, you're making more 2+ ions, but there are no more SO4 2- ions to counteract that change. So very quickly, this reaction stops, pretty much also instantaneously, because it becomes ionically unbalanced. So what the salt bridge will do is on this side it's going to pump in potassium ions. It's going to pump in potassium ions so that the sulfate ions have a positive ion to counteract the loss of the copper ions. And on this side, on this one, it's going to pump in chloride ions again to counteract the fact that you've not increased the concentration of the sulfate, but you've got more and more 2+ ions that you need. So the idea of the salt bridge is to keep the whole system ionically neutral. And this is why this is a filter paper or a non-conductive material. We want the electrons to go around the outside and do a job. So in place of the voltmeter here, this is where you could have your phone or any other device that's run off a battery. The salt bridge must be non-conductible or can't be conducting of electricity, otherwise the electrons would just jump around the middle and they wouldn't do the work that you want them to do. But it's a very important part because it keeps the whole system ionically neutral and the battery won't work without it. So explaining that in words, we've just done it for the zinc, but you could also argue it for the same idea for the copper. So the half cells are no longer at equilibrium because the zinc is becoming zinc 2+. So you get an increase in the concentration of the zinc 2+. And immediately that happens, the reaction stops because it becomes ionically unbalanced. So to achieve ionic neutrality, we need to increase the concentration of our negative ions to counteract the increase of the positive ions here. As I said, you could argue the same thing for the copper. In this case, the concentration of the copper 2+ would decrease, and again, we would achieve the ionic neutrality by pumping in more positively charged ions. Now, the best salt to use in a salt bridge is not actually potassium chloride. The best salt to use is this one, potassium nitrate. So that is always the best salt to use in your salt bridge. The reason for that is that potassium ions are always soluble, so you're not going to produce a precipitate, and that precipitate would either gunk up this end of the salt bridge or separate out, and that might cause a problem. And all nitrate ions are also soluble, so again, same argument, they wouldn't block the salt bridge and they wouldn't precipitate out. So let's look at what's happening to the half cells as the reaction proceeds once we've got the salt bridge in place. So the zinc, my half equation here is my zinc solid metal turning into zinc 2+ ions, and this is my source of 2 electrons. On the copper 2+ is gaining those electrons, that's my sink of electrons, to become copper metal. So the overall reaction is the zinc plus the copper ions becoming zinc 2+ and copper. It's your standard displacement reaction. This is aqueous and solid. So as this reaction proceeds, you get more and more of the zinc turning into zinc 2+ ions. So the concentration of the zinc solution increases because you're going from zinc to zinc 2+. This is wearing away at the zinc electrode. So the mass of the zinc electrode decreases. The electrons released by the zinc, they're going to travel round the external circuit to the copper electrode. So they travel to the copper electrode. The copper here, the 2+ is turning into copper. So I'm losing copper ions and I'm turning them into copper metal. So the concentration of the copper solution decreases. And because those copper 2+ ions are becoming copper metal, the mass of the copper electrode increases. Now, we can use that chemical energy that we've released here, this flow of electrons. This is the basis of all batteries, all fuel cells. It doesn't matter the size of the battery or what you're using, the basic electrochemistry is exactly the same. You have a source and a sink of electrons. You have a salt bridge and you allow the electrons to flow around an external circuit to drive something.